Hi, everyone. Good morning, and welcome to this week's webinar. It's just me this week. Daniel couldn't join, but he'll be back. And so this week, we're going to be talking about 3D printing end effectors. And before we get to that, an update from us at Markforged. We're going to be at Rapid next week in Detroit. So if you are in that area and you're planning on going, be sure to stop by our booth. We've got a couple new things to show off. That'll be pretty interesting. So make sure that you come check us out. So as I said, this week we're going to be talking about robotic end effectors, and I've got a slide deck that I'm going to share with you guys as we go through this. So as you probably know, industrial robots are an integral part to manufacturing today. I'm sure you've heard the term Industry 4.0 before, which is the idea of very agile mass production, where you have a lot of data sharing happening in the cloud between different robotic automated systems across multiple factories to really optimize how you're mass producing parts. And so right now, there are literally millions of industrial robots employed worldwide, over 2 million. And in the US alone, it accounted for more than 10% of the GDP growth between 93 and 2007. So this is not just a huge part of the manufacturing industry, but a huge part of the economy as well. And so end-of-arm tooling, or end effectors as they're also called, are arguably one of the most important parts of the robot. I call it the business end of the robot. It's the part that's actually doing the thing, as you could say. So without end effectors, they would have no way of actually productively interacting with their environment. And so they're usually customizable and modular, so you can switch different end effectors onto the same industrial robot arm. So you may have some grippers that are holding things, some may have tools on the end. And so today we're going to be talking about how you can optimize the production of these end effectors so that this critical component in your manufacturing line can be produced more efficiently. And so here's a closer up view of that end effector that was in that last picture. And so the idea is, with Markforged, how this fits in with 3D printing end effectors is it's making it so hardware is not the limiting reagent in Industry 4.0. So Industry 4.0 is this really agile optimization of manufacturing, the fourth industrial revolution. And if we can't make hardware faster, then that's still going to be the bottleneck in our manufacturing. So this is how Markforged fits in. So end-of-arm tooling, it comes, as I said, in many varieties. So a lot of factories, like automotive factories, they put power tools on the end of robots, and they're performing a bunch of different operations. Sometimes, as in that second picture, there's a vacuum gripper that suctions pieces and moves them from place to place. You can have magnetic grippers on the ends of robots. And you can also have just regular manual grippers that are physically gripping parts. And so although there's all these different types, they all have one main thing in common, and it's that they're typically very expensive. And the reason why is because grippers are manufactured in low volumes. So this means that first you have to design the part, and then if it's getting sent to the machine shop, you have to process the part in CAM, and then you have to send it to the machine shop to be machined, where it will probably wait in a queue. So that's skilled labor to be machined. And so then if a part breaks on your line, if you have an end effector that fails, then it can be a lengthy downtime because you have to wait for the part to be machined again if you don't have spares. And additionally, a lot of them are customized to be a certain shape or size. So having an end effector with a conformal geometry can be very important to make sure that you are consistently gripping parts in the same manner every time, because consistency is very important in these mass production processes. So here you see an example of these grippers. They have this curved geometry as they grab the inside of this pipe coupling so that they can grab it in the same spot every single time. And so before I move on, if you have questions throughout the webinar, feel free to throw them into the Q&A window, and then I will answer them live as we go through. So yeah, so you can see here, conformal geometries are something that are pretty common with end effectors. So how does 3D printing fit in? So with 3D printing, one of the most important things with end effectors is that you get complexity for free. And what that means is just because a part has geometries that normally would be hard to manufacture using traditional methods, in 3D printing, it's no harder to produce. It automatically gets sliced through the slicer with no cam necessary, and then gets produced on the printer automatically. Another important aspect is that there is minimal skilled labor involved. So instead of having a machinist who has to set up the mill or lathe, who has to process the files in CAM and then actually run the job, the printer is doing a lot of that autonomously. And then another advantage is shorter lead time. So because you don't have to have as much skilled labor going into it, and a lot of the process is automated, you can run prints overnight, you can run prints over the weekend, and they don't have to sit in a machinist queue. And so that allows you to get parts same day. And so this fits in really well with something I mentioned earlier, which is less downtime. So if you have a part that fails on the line, instead of having to have it wait in the queue to be made again, you could, number one, make the part same day, or number two, anticipate parts in the line that might wear out more quickly, and then you can make spares of that part and have just a bin of end effectors, which we have a lot of customers do, where if you have a part that's interfacing with production parts in the line a lot and might wear down, you can literally have a bucket full of spares that you just throw right back on the machine so that you can really minimize the downtime. And then, so another advantage is weight. So especially with 3D printed composite parts and even with 3D printed metal parts, which I'll get to in a second, the ability to make end effectors that are lighter weight than solid metal is huge, because the lower the weight of the end effector is, the higher the payload the robot can carry. So, and this is an example here where these end effectors, Dixon Valve is one of Markforged customers, and they make these end effectors that are conformal to the outside shape of these pipe couplings. They manufacture a lot of pipe couplings. And so moving these around on the factory floor, they need end effectors that are conformal to that shape, that can be made quickly and that are still tough and really resistant to wear. And so in this case, these ones were printed using Onyx, which is printed on our composite printers, and which works out very well. We have a lot of customers who use our composite printers to make really lightweight, really durable end effectors, and you can get them same day. So it's a really advantageous avenue to take to manufacture end effectors. But one thing to note is that they can wear out. So here's an example of an Onyx gripper jaw, and you can see it's interfacing with the inside of this coupling where there's threads. And this repeated interfacing with the threads is causing wear on the surface of the Onyx. You can see it's wearing in the same pattern as the threads. And so this brings up a good point where you can have composite parts that are very strong, essentially as strong as aluminum. But one thing you will not achieve with a plastic or a composite part is the surface hardness of metal. And so really, no matter how strong that part is, it will never be as hard as metal. And so this brings up the point of sometimes you do need end effectors that have that abrasion resistance and hardness. And so that's where metal 3D printing comes in. So here's an example of that same gripper jaw printed out of 17.4 stainless steel. And so the advantage of this is that you get all of the same advantages of 3D printing end effectors in composites, but with the additional hardness and abrasion resistance. So these metal grippers can grip the threads on the inside and still last through thousands and thousands of cycles. And so here is another customer example. I have a video for you guys. So these end effectors are also 3D printed on Markforged printers. And this robot is working in a sheet metal bending, an automated sheet metal bending room. And so its job is to take these small, intricate sheet metal parts and take them to the press where it gets bent, and then transport the finished part to a bin on the other side. And so the reason that it's important that these jaws are, I'll play the video again. The reason it is advantageous to 3D print these jaws is you can see that they have that taper where it's really thin on the area where it's gripping the part, and then it tapers. And that's because, as you see during this operation, the part bends and it has to reach in and grip the part again without interfering with the tooling. And so this complex geometry is something that would be really difficult to machine. It would be pretty time consuming, whereas you can just throw it on the metal 3D printer and do it without having to use your machine shop at all. And being able to 3D print it out of metal makes it so you can do many, many cycles without having a human interact with the physical machine. And so, here we go, next slide. So the company that is doing this is called Lean Machine, and they're a job shop that's in Canada, and they do a lot of metal fab. And so, and this is their end effector. And another positive of metal end effectors that are 3D printed on the Metal X system is that they're lighter weight than machined metal. And the reason behind that is infill. So parts on the Metal X are printed with a lattice structure infill. And so that allows a part like this one, for example, to be printed out of stainless steel, but be about half the weight of a typical stainless steel part. And so it still has that high strength and rigidity because it's got a lattice structure on the inside, but it's still very lightweight. All right, so this brings up another interesting example where there's something called hybrid grippers. And so these are basically mixing the technologies of composite 3D printing and metal 3D printing, the advantages of both to get a really optimized end effector. And so the idea behind this is you want the light weight of a composite part on the end of your robot, but you also want the abrasion resistance of something harder like metal. And so what you can do is you can design the body of that end effector, the main chunk of it that's actually going to attach to the end of your robot, and print that out of onyx or onyx reinforced with continuous carbon fiber. And then the part that's actually interfacing with your components, your production components, you can print that out of metal. And so this picture, you can see this example here, where you get to get all of the weight savings of composites and then plus the wear resistance of metal. And you can still, because it's 3D printing, get these conformal geometries for a lot lower of a price. All right, looks like we're getting some questions in here. Will the metal end of arm tool damage the threads on the product being picked up? So this is a good question. This has basically a question of designing the geometry correctly and then programming the robot to pick up with the correct amount of force. And so this was actually an interesting question on that specific project where the end effector was being printed out of metal. There was another idea which is similar to a hybrid part, where printing the part out of onyx, but then inserting rods into the part, that metal rods, like off-the-shelf metal rods, so that you have rods that are interfacing with a small surface area on the thread, so that way you get the wear resistance, but you don't have a ton of metal on metal contact. Let's see. How can we compute price of 3D printed grippers to machine grippers? So this is something that it depends widely case to case. So the reason it's usually advantageous to 3D print grippers is because whenever you are making something that's custom and it's in low volume, it's going to take extra energy to build that because you need skilled labor going into building a single unit of something. And so whenever you have a bunch of bandwidth going towards singular parts, the part cost begins to skyrocket. Whereas when you 3D print something, it's being done automatically. So when the part is printing over the weekend or overnight, you're not pouring money into someone making that part. And so especially with these more complex geometries. And so my answer to that question would be, the easiest way to compare it is to print a part yourself and machine a part yourself and compare the cost. It's not like it's always 10 times less expensive to 3D print a part than machine it. It really depends on the geometry. But the more complex and conformal the geometry is, the less expensive it is comparatively to 3D print it versus traditional methods. I hope that answered your question. And feel free to keep the questions running as we keep going. All right. Yeah. So as I mentioned, hybrid end effectors are a really good use of combining both 3D printing technologies. And the idea of 3D printing conformal wear pads in other manufacturing processes, not just with robotic end effectors, is something as well. Whenever you're transporting parts that are heavy or metallic that may wear down the interfaces that they're touching, 3D printing conformal metal inserts out of something wear resistant, like a steel, is something that can be very advantageous. All right, so that's most of the content I have for you guys. The main takeaways: custom end effectors, custom end of our tooling is critical to automated processes. And as we know, automated processes are critical to the world's economy as a whole. As I mentioned, 10% of the GDP growth in the US in a 15-year period in the early 2000s was due to industrial robotics and automated robotics. And so this is an industry that is exponentially growing. And as this industry grows, what we're seeing is a lot of the time, hardware is what's keeping it from really exploding. The software is there, but being able to quickly iterate on end effectors, being able to quickly swap in conformal geometries for different manufacturing processes that you may want to run on the same line, and spinning up those automated lines as quickly as possible is what gives companies the edge in that mass production. So 3D printing allows you to get faster, less expensive conformal geometries. So that gives you those more efficient, optimized manufacturing processes. It makes it so you have less lead time, less downtime, and as I said, spinning up automated processes quicker so that you can get a much higher throughput. And so that's all I have. I'm gonna open it up to questions if anyone has questions about the webinar. Says, what are the softest metals you print for end of arm tooling? So the metals that we are currently printing on our Metal X system are 17.4 pH stainless steel and H13 tool steel. And soon we are going to be coming out with A2 tool steel, and Inconel is coming out sometime soon, 316L. And so out of what's out there right now, 17.4 pH stainless steel is the softest metal that we have. And then, as I mentioned, it really depends on what you're looking for and what it'll be interfacing with. If you're looking for a truly non-marring surface that you want to make end effectors out of, then composites are going to be the way you want to look, because onyx is a non-marring surface. It's a nylon-based thermoplastic, so that's not going to be scratching the surface of metal parts that it's interfacing with. Question from Charles: which two of your printers would be needed to have the combined effector solution you mentioned before? That's a good question. So if you're unfamiliar with our product line, our metal system it's the Metal X, and that is our metal printer that we sell. And then we have an entire line of composite printers. And so it depends on what you're going to be making that end effector, the composite part of that end effector out of. If you want to be reinforcing it with our continuous carbon fiber, which is what gives you that aluminum strength, then you are going to be looking at the X7, which is our highest end industrial machine, and that's able to print in all of our reinforcement fibers. And the Mark II is our desktop version, which has a little bit of a smaller build volume, a little bit, the industrial one's a little bit more precise than the Mark II, but that also does our continuous carbon fiber. So you would probably want, so one of the ones from the composite line and then the Metal X system. Give some examples of printing cost per hour. So this is a good question as well. So this depends on a couple different things. It depends on the machine, so it depends what you're printing in, and then it depends on the geometry of the part. But most importantly, it depends on the machine and the material that you're printing out of. So if you are printing in a composite material, for example, if you have a ton of reinforcement fiber in that part, it's going to be more expensive than if you have if you're just printing out of onyx. But to give a ballpark amount, I rarely see composite parts that have a material cost that's over $100. Usually it's on the order of tens, depending on how much continuous fiber is in that part. In terms of cost per hour, I don't have an accurate answer for that. But if you're interested in learning about how much parts cost if they were sliced in Eiger, you can check out on our website. Check out Eiger, it's our software, our free slicing software that comes with our printers, and you can figure out how much your parts might cost. Oh, and then the second part of that question is in metal. So with composites, you're correct. You're really only paying for materials for the most part, power you could say as well, and then the time to set up and take the part off the printer, which is pretty minimal. Whereas with metal, you're paying for the materials. That's the bulk of the cost. And then there's a washing stage and then a sintering stage for that part. And so those add a little cost as well. And so that I would break down, that would make more sense to break down in cost per part, which would depend widely on the part, more so compared to cost per hour. Question from Gary, are there 3D materials for high temperature for 400°F applications? So you specifically mentioned PEEK. PEEK is a great high temperature material. We do not print in PEEK at the moment. We do, so our main thermoplastics are onyx. We have onyx FR, which we just released, which is our flame retardant onyx, and then nylon. And so our onyx material it's heat deflection temperature, which is one way to measure how heat resistant a material is. Its heat deflection temperature is around 300 Fahrenheit. And then we have a reinforcement fiber, high strength, high temperature fiberglass, which also has a heat deflection temperature of around 300 Fahrenheit. So what it mostly depends on is how long it's spending in that high temperature application. So if it's going to be at 400°F for hours at a time, then those composite materials might not hold up if it's under load and at that high temperature for that amount of time. But if it's reaching 400°F for a few seconds at a time and then coming back down, we've seen many applications where onyx has been useful. How large an end effector can your machines print, metal or composite? So on our composite printers, our largest build volume is about 12 inches by 10 inches by like 8 inches. That's on our industrial series, that's ballpark. And then in metal, so right now we have our sinter one that's out, which is a little smaller geometry, and the largest parts on that are about like 4 inches, 3 or 4 inches by 3 or 4 inches by about 8 inches. Let's see, do you have capability to print aluminum parts? If yes, what specified grades in aluminum do you print? So this is a question we actually get a lot, and this has a lot of different facets in the answer. So one, we cannot print aluminum. Aluminum is actually a really hard part to 3D print for a lot of different reasons. It's a really difficult material to sinter. And so at the moment, we do not print aluminum. And it's interesting because a lot of people who come to us who want to 3D print in aluminum actually end up buying our composite printers. And the reason is because aluminum is a material that for many people who use it, we use it because it's very easy to machine and has a pretty good strength to weight ratio. And so it's got decent material properties and is easy to fabricate with. And so we're really used to using aluminum. A lot of times, customers who typically machine out of aluminum buy a composite printer, and they can print parts that have about the same strength as 6061 aluminum, but at a lot lower cost than machining a part. And so we have a lot of customers, instead of looking to 3D print parts that they normally machine out of aluminum, and then printing them out of aluminum, they typically print them using our carbon fiber and are really happy with those results. All right, any other questions from anyone else? I'll give you guys another minute or so to throw questions in there if you have them. And then after that, we will wrap it up. Have you tried to hip your metal parts? I personally have not hipped any parts, but I do know, I'm pretty sure I was just talking to someone that was on our materials team, that our parts have been hipped before. But so there's a caveat to this. So as I mentioned, if you have a part that's got a lot of structure infill, hipping that part, I'm not sure how it would perform because you have some hollow cavities within the part. If you were to print a part, so on our printer, we're releasing the ability to print with a 50 micron layer height and being able to do full density for smaller parts, then those parts you would be able to hip. But then that's for those of you who don't know about hip, it's if you really want really high density in your metal parts, you basically apply this really high pressure to the part in like an industrial oven. And what that does is it gets you that like 99.9% density. Our parts, when they're printed, the parts that, the metal parts are about 95% dense or so. And that's due to the process that we use where it's extruding a metal powder mixed with a plastic filament and then sintered down to the correct size to the full metal part. And so our density, we don't reach the same as hip through our furnaces. But that's a good question. I personally have not hipped a part. Do any of your composite printers allow use of soluble supports? So the supports that our printers use are just manual removable supports. So what we recommend is when your part comes off the print bed, you can just remove them by hand or with pliers. And typically it's no problem at all to do that. And it's the same material. So onyx, if you're printing in onyx, the supports will be printed out of onyx as well. All right. If we've got no more questions, I think that will wrap it up for us. Thank you for joining me this week. Next week, or next time we broadcast, probably in a couple of weeks, we'll have Daniel back most likely, and we'll be talking about more metal applications. Oh, it looks like, let's see. Have any of your customer parts ever been used for primary structure in spaceflight? So not that I know of. I know that we have a part that was used on a balloon that went up into like the stratosphere, but I don't think we have no structural parts on spacecraft yet. But it's interesting. As I mentioned, we did just come out with Onyx FR, which is really exciting because it's one more step forward to breaking into the aerospace industry. 3D printing in aerospace is something that's pretty new because there's a lot of really stringent what's the word I'm looking for? Really stringent requirements for parts. And so with 3D printing parts, especially with the FDM style process where you have infill, it's really hard to run FEA on those parts and to have a reliable actual safety factor on them. And so that's number one. Number two, being able to make parts that are flame retardant, that don't propagate a flame. And so we took a step forward with that with Onyx FR, which is really exciting, as that's a material that we talked about a couple weeks ago that doesn't propagate a flame and is flame retardant. So we're going to start to see more Markforged parts in the aerospace industry, which is really exciting. All right, and this will be the last question we take. I might have missed this one. What AM technology is used to print parts with composite material? So on our composite printers, it's a FFF process, and basically like an FDM-like process. And so specifically with our continuous fibers, it's called CFF, continuous filament fabrication. And so the way it works is it has two nozzles. One nozzle prints the matrix thermoplastic material, which is onyx or nylon. And then the other nozzle lays down continuous paths of fiber, which is carbon fiber, fiberglass, Kevlar, or high strength, high temperature fiberglass. And it tacks down those continuous fibers within the part in whatever orientation you choose to give it the strength in whatever direction it's going to be loaded in. And so the technology is very similar to the FDM process if you're familiar with how those printers work. So I think that'll wrap it up for us. Thank you for joining us, and I'm looking forward to seeing you next time. Have a good weekend.